then I can normally do this. Yeah. So, welcome to this talk. So I would like to present to you some joint contribution with Marco Forgione, which is just sitting next to me. He's visiting us here in Lyon for 1 week, and he's from ITSIA in Lugano in Switzerland, which is an artificial intelligence center. And here I would like to present to you some results on another so-called data-driven control method. And it's not the same type of method Simone is presented to you. It's more on an experiment-based control design method, but I will try to impose some safety constraint on this using models. Well, it's a control problem, so we wish to determine a controller for an unknown true system, and this true system could be complex and could be a nonlinear system. And we, as for Simone, we don't know anything about the system. And the controller we want to design is parameterized. So in fact, what we want to determine is the coefficients of that controller. So for example, the coefficient of a PID controller. So if our objective is to determine that particular controller minimizing a certain objective function v theta. So for each controller, you have an objective value, and this objective value is the objective function is a measurement of the loop made up of the controller k theta and this unknown true system. So for example, v theta could be the energy of the tracking error. So and we would like to minimize it. So that's why we minimize it. So v theta, a small v theta is a good performance. But of course, v theta, since it's the performance of the controller on the unknown true system, v theta is unknown. So in classical model-based control design, well, we use a model of S to approximate this unknown v theta. So in fact, we try to find a controller which minimize the which gives the best performance on the loop k theta model, the loop made up of the model and k theta. So we replace, in fact, the unknown S here by M, and we then evaluate a new objective function for that. So that's classical model-based control design. So in this data-driven or experiment-based control design, in fact, you will approximate v theta by making multiple experiments on the true system with different controllers. So you choose different controller with different theta, you make experiment on the system, and you will, based on that, derive a model of v theta. And once you have a model of v theta, you can design a controller by minimizing it. So how can we do that? Well, so when we do an experiment with k theta on the system, well, we can get a measurement of v theta. So for example, if it's v theta is the energy of the tracking error, well, when we make an experiment on the system, well, we can then estimate this energy. And so that would be then the measurements of v theta. And so as I told you, we do that for a number of time. So we get a number of these data pairs. And in this pair, we have the coefficient of the controller and the corresponding measurement. So we have that for a number of time, let's say 50 data points. And so based on this data, you can imagine that you can get a model of the static function v theta. V theta is not dynamic, there is no dynamic inside. So based on this, it's quite easy to find a model of v theta. You could use polynomial model structure, but generally in this type of experiment-based control design, they use a non-parametric approach, non-parametric model, which is called Gaussian process. And so basically the main difference is here we use a model of the true system, and here we don't use a model of the true system, we just use a model of the cost function. So well, then, of course, the question is, how do we collect this data? How do we determine the sequence of experiments we have to perform in order to get the best controller? Well, that's what's done. That's done generally with global optimization algorithm, and more particularly an algorithm which is called Bayesian optimization. I will give you some. I will try to explain to you in a simple way Bayesian optimization. But so all these things is very well known in this experiment-based literature and so in machine learning. But now, what did Marco and I contribute to that? Well, of course, when you do all these experiments, you may test controller that pose safety issue. Because in a sort of way to learn V theta, you can test a controller which, for example, destabilize the true system. And so that's really what you would like to avoid in practice. So, and this is a well-known problem in this literature, and generally it's addressed with by making some assumption on V theta, for example, assumption on its maximum gradient. And so if you assume that you know the maximal gradient of V theta, well, then you may infer that that you don't want to apply a certain controller. But we want to here we'll propose an alternative approach. Which will based on a nominal model of the true system. So here we bring back a model, but this model should not be a very accurate one. So we'll not use that model for control. We'll just use it to determine a safety zone for experimentation. So to say, well, that controller, you will not test it because it may be dangerous. So before showing you how we will do that, let's talk a little bit about this Bayesian optimization to determine the sequence of controller that will be tested on the system. And so what does Bayesian optimization? Well, the objective is, a clear objective is to minimize this objective function. So to find the theta which minimize this objective function. And we'll do that with a number of iterations. Of course, we'll never get the global optimum. We'll get at best a good approximation of the minimum. And so you have a number of iterations. So let's say 50 of these iterations. And let's say we are iteration I, iteration 10. Well, at iteration 10, we'll do some steps. And the first step will be we'll make an experiment on the system with a given controller. So, and this controller is parameterized by theta I. And well, by doing this experiment, we can get the measurement V tilde theta I. So, in fact, by doing this, we get a new measurement pair theta I V theta tilde I. So, new measurement. So that gives you the possibility to update the model. And so you will update the model, which is this non-parametric model of V theta, and you will use the data that you have collected up to this iteration. So iteration 1 up to iteration I. So if you have iteration 10, well, then you'll have 10 data points, theta k, V tilde theta k, and you will estimate then the best model for V theta based on this data. And the Gaussian process allows you to give also a measurement of the uncertainty of the model. And so, well, we have a model, and then we use that model, in fact, to determine the next controller to test. So the next part of the iteration will be to determine the next parameter to test, theta I plus 1. Theta, if we was at iteration 10, well, that will be the theta we'll test in iteration 11. And so for that, we'll maximize a so-called acquisition function. And the acquisition function, well, basically it's it will be built based on the model we just the last version of the model based on the data collected so far. So yeah, well, I don't want to give you so much expression about the acquisition function, but I just want to say to give you a flavor on how this next point will be chosen. So in fact, the next point will be chosen. The next point will generally be a point where the model says, well, the cost function will be small. So a model where VI theta t is small. So because VI theta is a model of V theta, well, then that makes sense to test the controller where you will have a small value of this model of the cost function. And also, that's in fact, there will be a trade-off between this type of theta and a theta where you have a large uncertainty. So where the model of VI theta is large. So in fact, where the uncertainty will be large, well, it will be large in the region of the theta space where few theta has been tested. So of course, you have tested here 10 points, but that may some region in a theta space may not have been covered. And so, well, then the model will show a large uncertainty. And so maybe it would be good also to test the theta in there, because then you will be able to improve the model of V theta, because you will cover more the theta space will be more covered. And so in fact, it's a sort of the acquisition function makes a trade-off between exploitation by using the model as much as we can. So that's the exploitation. And the exploration is, well, trying a point that has not been tested in order to improve the model. So I will give you a little example of this trade-off in the next slide. But let's say after we do these experiments, this iteration for 50 times, and at the end we stop. And so what will be the best controller? Well, the controller will be one of these 50 theta, will be parameterized by one of these 50 theta. And basically, you can take the theta which has given you the best performance in practice. So that should not be the last one, but you take the theta which has given you the best theta in practice. So that's the classical Bayesian optimization. So let's see a little bit how this trade-off is made and what is the Gaussian process. And so let's say we are iteration 4, so I is 4, and we have thus collected, and let's say that the controller is only parameterized with one parameter. So that's the parameter of your controller. And since there is only one, I can represent this in a nice plot. And here I represent V theta. And so that's the unknown cost function. That's the black curve here. So that's this unknown. So that's the performance of k theta on the unknown truth system. And so you see that the optimal controller is here for a controller which has a value of -0.4, sorry. And so at the iteration 4, we have tested 4 theta for controller. So that's controller 1 around 2, a controller around 1.4, a controller at around 0.6, and a controller around 0.5, basically. And we got these 4 measurements of the performance. And so based on these 4 measurements, we could deduce the blue curve there, and that's the model of V theta deduced with Gaussian process. And so, and in the shaded area there in light blue, well, that's the uncertainty of the model at each theta. So effectively, you see the uncertainty is very large in this region is because you have not tested a lot of points here. And so in fact, the Gaussian process just extrapolate the value of V theta here, but there's no information there. So you get a quite crap estimate of the truth system. But that is, you also see that the uncertainty is quite large. So now, well, in fact, in order to design, iteration 4 remains to be done. What remains to be done is to determine the next point to test. And so what could we do? Well, we could test somewhere where the model is small. Well, that would say that we should test here somewhere. But it would be maybe a good idea also to test where the uncertainty is large. So basically here. Why? Because in fact, you see that effectively the model says that here V theta would be larger than this value. But since the uncertainty is large, well, you could also gain a lot because, in fact, the value of v theta could be also as small as this. But you could lose also a lot because the v theta could be as large as that. So that's sort of a gamble all the time. But sometime in this Bayesian optimization, you do a gamble. And so, well, in fact, the acquisition function will make a trade-off between testing here and testing somewhere where the uncertainty is large. And so in the next two iterations, in fact, you will test 2 points, one which is there and one which is here at -0,1. And in fact, at that moment, the acquisition function will be maximized at 0,1. So it's somewhere here where the uncertainty is large. But you will, the iteration 5, well, you will have a point which will be there. And so iteration 6, we have 6 points now, one there, one there. And so you see that with the 6 points, well, the estimated model is much better already. You see that you start to understand what happens in this region, that you can gain, that you could have really a minimum here and no longer there. And so here, well, what would do the acquisition function? It will take, in fact, a point where you have a large uncertainty and where you can gain, in fact, the most. And so it will be somewhere here at around -0,4. So that means that the controller that you will test at iteration 7 will be, in fact, the optimal controller. And so, well, that's what happens in this iteration, and you can continue up to 20, and at a certain moment you stop. So you had only a sort of budget for 20 experiments, but so effectively it's that classical Bayesian optimization. So that's quite something which exists, in fact, in the literature, and what we have contributed somehow is to have, because in fact when you test here, you could effectively test here. And if you have no chance, you could have a controller which gives you a very big value of v theta. And that could be even worse in the beginning of this iteration. So in fact, what the Bayesian algorithm may test controller that pose safety concerns. And so how to avoid that? And so here we propose to use a nominal model of the unknown dynamic. So as I told you in the introduction, this nominal model should not be very precise, that's the way we will be able to avoid these bad controllers. And so we'll define a safety zone based on that nominal model, and we'll denote that theta safe, and we'll ensure that only controllers in this safe region will be effectively tested on S. But to define this theta safe, we will use a rationale, and you can agree on this rationale. You can disagree with it, but our rationale would be this the following one. So if a given controller gives very bad performance on the model, well, this controller should not be applied on S. So that will be the rationale which will allow us to define theta safe. So, well, then, of course, defining theta safe is not complicated. And so you will define theta safe as the older controller for which the performance of the controller k theta on the model is acceptable. And so you define that as all theta such that the performance of k theta on the model is smaller than a certain threshold. And so if Vm theta is larger than that threshold, well, that means you say that this controller is really bad. Bad performance is performance which are higher than V safe. So, well, this set is completely defined because everything is known. I know the model, I know k theta, so I can define this controller, this set of controller without problems. So now let's come back to our problem. We want to find the minimum of v theta, but we want to do that by only testing controller which are in this safety zone. Okay, how do we do that? Well, what we proposed is to, in fact, not applied the Bayesian optimization algorithm on v theta, but on a modified cost function. And this cost function is j theta, and it's defined like this. Of course, j theta should be related to v theta, and it is. So it's v theta when you are in the safety zone, when theta is in the safety zone, and then it is equal to another value when you are outside of the safety zone, and this other value is well, the performance on the model. So first of all, before explaining why this is an intelligent move, well, first look at it. So minimizing this will give you the same minimum as v theta if the optimum value of theta is in the safety zone. So that means that you really have to define this really badly. You have a really bad model to say that the best controller on the true system is a controller that gives you a very bad performance on the model. But if it's not that bad, well, then you will have the same minimum from these two optimization problems. But why this allows you to avoid testing in the testing controllers that are outside of the safety zone? Well, first, let us note that if we want to apply Bayesian optimization on j theta, well, we'll derive a Gaussian process of j theta, and not of v theta. So that's the difference. And so in order to define this Gaussian process, well, we'll need to have measurements of j theta at different theta. And so how do we get this measurement? For example, at iteration I, we have to we have defined that we have to test the theta I. So we have to define the measurements of g theta at theta I. And so how do we get that? Well, we get that in this way. So the measurements at the to-be tested controller, well, it will be the measurement on the true system, so v tilde theta I. So that's an experiment of k theta I on the true system that leads to the measurements v tilde. And you will do these measurements if theta I is in the safety zone. And if it's in the safety zone, well, you are allowed to do this because you are safe. But if you are theta I is outside of the safety zone, and that you know perfectly because the safety zone is entirely defined by the model, well, then you will not test on the real system, but you will test on the model. So you will do a simulation on your computer and replace the unsafe measurements on the true system by a measurement on the model. And so in this way, well, if in the sequence of experiments theta I does not lie in theta safe, well, we don't do the experiment on true system, but we do a computation on the model and get the measurement in this way. Okay, so that's basically the idea. So let's see if it works in practice. And just a little remark, in fact, in order to put even more stress on this constraint of safety zone, we have added an extra constraint. But anyway, that's not so important. So just the result I will show you is with an extra constraint. But we have also made an experiment with just without the constraint and give you similar results. Okay, so let's go to the example and let's start with a linear system first, and then let's go further to a more complex example with a nonlinear system. So in this first part of the example, the true system S is just a transfer function. It's a second order system. We have some measurement noise. And then the control problem we are looking at is a tracking problem. So we will put here a unit step. And we wish that the output here is close to a desired output. And the desired output we want is this way. So it's the step response. So C here is the unit step you are there. And here's that's the desired closed loop transfer function. We are in model reference objective. So we have a model of the closed loop transfer function we want. And that gives you the desired output. So, well, what does that mean? Well, we want that y settled in about 1 second, and the overshoot should be smaller than 5%, or should be equal to 5%. So, and we want to realize that with PID controller. And the denominator is fixed, as you can see, because there is an integrator. That's why that's to get no static error. And well, the pole here is determined with the objective function. So that's this 4,2 is just this 4,2. So that's related to the closed loop transfer function we want. And so what is theta? So what are the parameters we have to tune? Well, that's the gain of the PID controller, as well as the 2, 0 here, P1 and P2. And in fact, it's if we know P, well, it's possible to get this closed loop transfer function by just compensating the poles of P. So if you put P1 is 10 and P2 is 1, and you tune the gain intelligently, well, you can find that the closed loop transfer function from C to Y is exactly this. But of course, you don't know P, and so you cannot do this in practice. So, well, so that's the control problem we have. And well, to define the safety zone, we have to have an initial model. Well, we have this model where the poles are not correct and also the gain is not correct. So it's not particularly a good system. So now let's see how we can run our Bayesian optimization. Well, for that we need measurements of the cost function. Well, in fact, if we want yt to be close to y des, well, it would be good to define v theta as sort of the energy between the energy of the difference between yt theta and y des. And so if you do an experiment with a given k theta and with here a reference, which is a unit step, you can measure yt theta in a discrete way, and you can compare it to y des and evaluate the energy here based on the experiment. We'll do an experiment of 5 seconds because we want to reach the steady state in 1 second. So that should be sufficient. And so we get this this estimate of based on experiment, we can get an estimate of the performance we want to minimize. And we can also define a safety zone. Well, that's the classical way to define a safety zone. And since we VM theta is evaluated on the model, well, we can, if we put here the model, well, we know the closed loop transfer function between a C and Y. Well, this is a classical complementary sensitivity function, mk over 1 plus mk. And so ymt theta is just the impulse, the step response of that closed loop transfer function. You plug that in this equation where you compare it to the desired value, and you compute the energy over an experiment of 5 seconds. So that's you put an even higher value if the loop is unstable. Just that's really not necessary, but that's how we programmed it. And we put a sort of threshold of 0.1, which is quite high value with respect to the value we'll get in practice, in fact. So about 20 times higher than the values we'll get at the optimum. So it's really a threshold, not to say that it's good performance. 0.1, it's above 0.1 is really bad performance. Okay, so we have optimized this then, J theta. We will do 300 iterations. We'll make 300 evaluation of J theta. And we'll start with something. And what we will start with is the controller that gives you perfect performance on the model. So, well, then you have to compensate the two poles of the model and tune K. And if you do that, and the K would be 0.75, you see that you compensate the two poles. And then if you put that controller K theta init on the model, well, then you have a perfect match between Ym and Y des. So there, Vm theta init is 0, but the real V, because when we test this theta init on the real system, well, then you are far away from the desired output. So that shows that the model is not that good, because the desired output is in red here. So that's this settling time in 1 second, small overshoot of 5% here, and then you you go to 1. And with the initial controller designed with the model, the initial model, well, you get here this curve, which is much higher overshoot, and the settling time is much higher also. So now we do this 300 experiments with Bayesian optimization, and then at the end we get the best controller in this 300 optimization is controller design with theta opt. And that's the black curve when we evaluate it, and you see, well, we in fact have found the real optimum. So what conclusion from that? Well, optimizing J instead of the real cost function, well, that does not prevent us to find a good optimum. But what the good news, the other good news is that it has avoided some bad controllers. So in fact, by evaluating J theta, we on the 300 experiments, 300 iteration, well, in fact, 30% of the to-be tested theta were outside of the safety zone. And so that means that we have only evaluated 270 controllers on the true system. And these 30 controllers were not tested on true system, we just tested on the model. And what did we avoid with that? Well, in fact, 5 of these 30 controllers destabilized the system. So we have avoided instability. So that's quite good news. And if we would have evaluated this 30 controllers on the system, but that we didn't do, but if we would have done it, well, the average performance or the average cost function for these 30 controllers would have been 400 times larger than the average value for the tested controller. So we have really avoided controllers that give you really bad performance. Okay, you could say, well, all this is quite easy because it's a linear system. You don't need all this stuff to get a good controller. But let's complexify a little bit. So let's see that we have a nonlinear system. Well, it's still simple, but we have here a Hammerstein system. So the Hammerstein system is static nonlinearity at the input and then a linear system. So the linear system, it remains the system we had before. And the nonlinearity is just a saturation at 1.5. And so, well, that's the true system. And you will see that we need to hit that saturation in order to get a good controller. The best controller will lead to U, which will hit the saturation. But otherwise, we can run exactly the same Bayesian optimization and also 300 iteration. And the safety zone is defined based on a linear model. So the true system is nonlinear, but the model we use to define the safety zone is linear. And it's the same as before. So we do the 300 experiments and we get these results. So, well, theta init is still very, well, it's not good. So, and it's even worse than in the linear case. In red, you have still what we want, so that's desired output. In black is the best result we have after 300 iteration. So you see that beside small, it's a little bit slower in the beginning, but then afterwards we get exactly to YDES after 1 second. So we are quite close to YDES, but we are not completely on YDES because so that's yeah, the problem is a little bit more complex. And just to show you that finding that optimum, the black optimum there, it's not that easy. If we would have designed the controller, supposing that the true system is P, and we neglect the saturation, and we suppose that we know P, well, so then we get the green curve here, and you see that this green curve designed based on the linear model, well, is not as good as, well, it's far from being as good as the optimum we found with Bayesian optimization. So the black curve is much better than the green curve. So optimizing J instead of V does not avoid us to find a good optimum. And it has also been another advantage is that we've avoided some bad controllers also. Here, 40 controllers on the 300 were outside of the safety zone, and thus they were not tested. And in these 40 controllers, well, there were experiments with controllers which not unstable, but who yielded a limit cycle. So I can show you what this performance is. So here, for example, one of these non-tested controller, here you have the desired output, and that's the output with this limit cycle controller. So that's not such a good behavior. So you have avoided 5 behavior like this. And also, you have also got, if you average the performance that we would have got with these 40 controllers with respect to the performance we got with the average performance we got with the 260 controllers that were really tested, well, we have a factor 9. So here the factor is less than the 400, but because the limit cycle is much less, well, before we had instability, so you divert much faster. After 5 seconds, you are really already very high. But here it's a little bit less high, but still you avoid big, so the V for the controllers that were outside of the safety zone were giving very bad performance, and not testing them has not prevented us to find a good optimum. So that's basically our little contribution on this topic. So if we summarize, we have added safety constraint in experiment-based controller calibration. And we have done that based on a nominal model knowledge. And so we are continuing this forward. That's also why Marco is visiting us. So, and we are looking at adapting the model during the iterative process. So if you want to have more information on this, we have published a paper in a conference, and it's also on HAL. And so, well, that's the end of my talk. So if you have any questions, please do. And well, I just want also to remind to all PhD students attending, our next event is the Spring School on System Identification. And so there's still a possibility to register till the end of the month. And we'll have Martin Skaukens as guest lecturer. So Mathieu, I give you the floor.
Thank you, Xavier. Thank you for your presentation and the recall for Spring School. Maybe somebody have a question.
I may try for a question. Actually, first of all, a remark. I mean, thank you very much, Xavier, for your presentation. Very interesting, and I like very much the way you bring the equations to life. Yeah. So, can we conclude by saying that actually we need a bad enough controller to be able to identify the model, but that controller doesn't have to be very bad. I mean, it should not destabilize or bring to limit cycles the closed loop.
Yeah, that's of course. I see your point. Of course, what we want to avoid is just that. Of course, testing a bad controller, you will learn in a region which are not really interesting, because you want to learn. Of course, here if I take back this this curve. In fact, you don't want to learn here. If you have a bad model here, that's not really interesting, because you are you will not find the optimum of V theta here. What you want to learn well is where V theta is small. So learning in region where V theta is large, well, that's not really interesting for our purpose, because in fact we want a good model in the region where V theta is small. And so, in fact, what we so if the threshold would be here, so in fact we replace the true curve in J theta, we replace the true curve by the model-based curve, and so so we hope that effectively it will, the two curves are quite close, but not it should not be that close. But see, if you see, you keep the region here. If you put here the level, you keep all that region to learn, and that's the interesting region, in fact. Yeah, because it's there where the minimum is, and so that's if we do G theta, you see that in fact it's V theta for all Vm theta smaller than V safe, and so let's, for the sake of the argument that Vm theta is perfectly equal to V theta, well then, in fact, it's just G theta is then perfectly also equal to V theta, but you will never test on the real system in this region because you will replace it by the model evaluation. But of course, the Vm theta is not equal to V theta, so it's important to test on the real system. And in fact, it's important to test in the region where V theta is small. But effectively, for the exploration, you have to test in the region where you hoped that V theta will be small. So it's somewhere where you have already a small value of Vm theta. You see, it's the Gaussian process model here, or the Gaussian process is small, and you have a large uncertainty because there you hope that you will gain a lot. Because if you had a large uncertainty here, well, even if it was large, you will not gain much because what you could gain here, it's up to that moment, and that's still higher than that point. But here it's smaller than that point, so that's where you want to test. In fact, you want not to test where you cannot gain, because here you will never gain something because you have already a point which is smaller. So even if you would get a V theta which was here, well, you will not gain because that would be higher than that point. And so, well, I don't know if it's the answer to your question, but
yes. Thank you very much, Xavier.
Somebody else? Xavier, I have a question about how can you avoid to test an unstable controller? You can only choose a small V-safe in order to avoid unstable controller.
But an unstable controller, if for example the controller K theta destabilize VM, well, if VM is the tracking error, so you put here M. If it's destabilizing, y T theta will diverge, and so effectively the difference between this diverging signal and y dash will be very big, and so the energy of that signal will be very big. So effectively, it will be larger than V safe, because so the VM theta for a destabilizing controller, well, is basically something very big. But it's not infinite, because of course you would take only you can take a simulation of 5 seconds, but it will be a very large value. You have to see if maybe VM is sort of if it's small, it's good. If it's big, it's bad. In fact, so that's why we put smaller than V safe with a destabilizing controller. Well, VM this will be big, and we put even a bigger value here to in fact, this is not so important. You could have removed it. At some point, we make all the test, but here VM, this quantity will be already larger than V safe. And so effectively, this 5 destabilizing controller here, they gave a VM which was larger than 0.1. It was I don't know. It was something like 1,000 like this. So it's not. So in fact, we see that K destabilize M, and so we don't apply it on the true system. And so we replace in the Gaussian process. We say, well, we have made the measurements; it's 1,000, but and so he knows that this value, no, there we don't have to test anymore because it's much too high. So that's the bad region, so we don't test there anymore.
Okay.
So, well, I guess there is no more questions. So, on behalf of Mathieu and Rachid, I would like to thank you all for attending this study day. And so, don't forget to So don't forget to tell us if you want to submit something at the SAGIP at the Congrès de la SAGIP, because I would like to have a sort of idea of how many papers we could expect. So, and if you have any remarks on the Congrès de la SAGIP, since it's the first Congress, well, we have to learn from experience. So, if you have some remarks,
Xavier, can you please just stop sharing? I'd like to share with the webpage of Congrès de la SAGIP just to